All right, so we're going to start Chapter 8, which, in my opinion, this is my opinion, if you look at the entire course of Cal 2, you should have about a third. It should be broken up into thirds. It's about a third of it is the techniques of integration, and then the middle, it's not even quite a third, is applications. And then the last should be series. And there's some other little things in there at the end that we might get in there. But I think we're at a good spot right here. Starting where we are, I don't feel like we're rushed yet, but I'm sure we'll try and rush through Chapter 8 at some point. So Chapter 8, it's different. It's different, yeah. You're at the last stretch here, yeah. I still haven't decided. I still have time, right? When's it supposed to be?
Oh, I don't know.
I think it's supposed to be 15th is the drop date, right? 2 weeks? Yeah. So, I don't know. Let's see how today and next week go. Let's see how much information I could possibly have on it. Okay, Chapter 8. So I wanted to get the whole Chapter 8 motivated with just some, where we're headed with it, where it's going to get us to. So if you have a calculator, I'd like for you to type in, if you can use your phone right now, it's fine, just put it away when you're done. I'd like you to type in sine of 4 and tell me what you get. -0.756. Negative what? 0.756. Anyone else? Approximately? Right? Anyone get anything different? Are you in degree mode or radian? You need to be in radian, right? Because if it were a degree, I'd have to put a degree symbol up here. Yes? All right. What's sine of pi over 2? Now, you didn't need your calculator for that, right? But yes? But your calculator agrees? It does. It should be. Okay. So we know how to get sine of pi over 2. We think about it, we can say 1, right? But if I ask you to do sine of 4, you're not going to be able to tell me. So you go to your calculator. So my question is, how does your calculator know it's about negative 0.756? What is your calculator actually doing? Is it drawing a right triangle and trying to come up with a ratio? And because isn't sine like opposite over hypotenuse? And so your calculator's not sitting there thinking about it like that, right? Does it, what does it do? So what can a computer do?
Run a logarithm.
What's that?
Run a logarithm.
Yeah, I mean, that's it. It's just going to, what did you say, logarithm?
Logarithm?
Algorithm, yeah, there you go. I think that's, yeah, I was trying to think of what you were trying to say. That's why I was like, okay. Logarithm, algorithm, same shit. Okay, so it's running an algorithm, and it can only do 4 operations: addition, subtraction, multiplication, division. That's it, right? It's all your calculator knows how to do. So what is it doing? So I'd like for you to look at the board here. That's our sine curve, right? We know that from pre-cal. We know that from Cal 1. We know that from Cal 2. There's the sine curve. What I'd like to do is I'd like to show you my approximation to this sine curve. So I'm going to try and come up with a new curve that approximates that sine curve. All right? And you can let me know whether or not you think my approximation is good or bad. All right? So here it is. You can see it up here. I've written what the function is. It's hard to see, actually. X. So I'm approximating it with the diagonal function y equals x. Would you agree or disagree with the statement that my approximation is good?
Yeah.
You think my x is good?
Trying to get it as close as possible, right?
I'm trying to. Does that black curve, is it close to the sine curve?
No.
I mean, it may be at the origin, right? Maybe at the beginning, like in here, it's close. But as soon as I make this turn, right, it's not a good approximation. So maybe there's another, maybe I can make it a little more complicated. How about if I use a cubic function, specifically x minus x cubed over 6, is that approximation better? Yes? All right, and what I've done is I've left behind the dotted one is the x from the previous function, right? So I've left that behind. Maybe I can get even better. How about this 5th degree polynomial? So can you see it up there? X minus x cubed over 6 plus x to the 5th over 120. That's even better. Wonder if I could go even better than that. There's a 7th degree, 9th degree, there's an 11th degree, there's a 13th degree, there's a 15th degree. In fact, I can just keep going with this, right?
Wow.
And I'm getting pretty close, right? We do. We need. We do need to find. We are going to be able to find out what that is, that function. Now it looks rather complicated, doesn't it? It's turned into x minus x cubed over 6 plus x to the 5th over 120, blah, 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 all this stuff, right? And that looks pretty intense. So here's the main idea, is that if you have a function that is continuous, so it's behaving nicely, then we can always approximate that function with a polynomial function. So do you see that that is a polynomial function up there? Right now it's a degree 29. It's a degree 29 polynomial. I can approximate any nice continuous function with a polynomial. The higher the degree I go, the better my approximation will be. And in the real world, that's enough, because a lot of times we just need things to be within a certain tolerance. So what your calculator is doing right now, sine 4, is it's plugging in 4 for x into a polynomial function. Because x minus x cubed over 6 plus x to the 5th over 20, that can be done easily by your calculator. That's multiplication, subtraction, addition, right? That's all that is. So you don't need to do it now, but if you were to plug 4 in for x right here, and then do minus 4 cubed over 6 plus 4 to the 5th over 120 minus 4 to the 7th over 50, 40. If you did that, I would bet you that your answer will be close to this. And the further you go out, the more decimal places you're going to get. Okay? And your calculator does that to a certain point and stops, because your calculator can only store so many digits, right? So it at some point cuts it off. That's how all computers work. So it would be important for us to be able to come up with that polynomial function so that we can use a computer to do the work for us, right? Understand that? Even better, though, is that it turns out that if you want to integrate that function, we want to integrate sine. If I want to integrate the sine function, I don't need a calculator or a computer for that, because I know what the antiderivative of sine is, right? But what if this function is something more complicated, like sine x squared? Now that you wouldn't be able to do. And I told you this already, that if I just throw a function out of the bag of functions at you and ask you to integrate it, chances are you won't be able to. But I'm telling you, if it's a nice function, that there is always a way to represent it with a polynomial function. And imagine replacing this with some polynomial. Can you integrate a polynomial?
Yeah.
Absolutely, it's just power rule. So integration becomes easy if you can get this conversion over to a polynomial. And differentiation the same way. If I want to differentiate it, it would be easy. Understand? Now this is based on something called the I'm going to mess up the name. It's Weierstrass Theorem. Okay, Weierstrass approximation theorem, which says basically that we can approximate any continuous function as closely as we ever want to with polynomial. And if that polynomial goes and we let it go forever and never stop, it is the original function. It is the function. So we can actually define the sine function as an infinite polynomial. And that is what's called its power series representation. So you have sine x the way we know sine x, and then we have sine x in its different form, which is called its power series representation, and that's what this chapter is about. How do you get to a function's power series? All right? But to get there, to get to this, we have to do a lot of stuff before we get here. E works the same way. I think I have other functions here. 1 over x. So the red one is 1 over x. I'm sorry, 1 over 1 minus x. Here are my approximations. What do you think? Better? 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 Hey, what's happening though? Do you notice a difference on this one? It's not going past some, at some point it's actually not good, right? It's not good to the left of what? It looks like 1. Do y'all see that? Compare that to up here. It got better. It just went out both ends and it just got better and better and better and better. But on this one, it seems like I'm stuck between, what, +1 and -1? Between +1 and -1, I've got a good approximation, right? Outside of that, my approximation doesn't work. Well, that turns out to not be a problem because all we have to do is shift it. All I have to do is move it. I don't think I have it set up on this one to move it. No, I don't. But you know how you can shift any function left and right? Back from college algebra? You just subtract a number and it moves it to the right, add a number, it moves it to the left. That's all we would do. We would just move the polynomial around and then the approximation would work anywhere. But because we actually have this little interval where it's good and then an interval outside where it's not good, we actually call that the interval of convergence. And so we'll talk about that later too. The sine function that I approximated doesn't have a restriction. So the interval of convergence is everywhere. Here, this one actually has an interval of convergence. Oh, e to the x. E to the x. Let me show you an approximation here. Good? Better, 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 better. Ooh, that's real good, isn't it? That's really, really good. This one, the interval of convergence is everything. So that one's going to work. We don't have to shift it. Take a look at that for a second. I'm going to write this down. Check out how awesome this power series is for e to the x. E to the x is equal to 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x to the 5th over 120 plus ... right? It appears that if this polynomial kept going, then I would have, I'm telling you, that's what e to the x is, all right? Where these numbers come from is what we have to figure out, right? We have to figure out, like, where are all these numbers? Like, why isn't this 5 instead of 2, or, But if you just will for now, take this on faith that this is it, okay? I want you to check out something that's really awesome. What is the derivative of e to the x? It should be itself, right? I'd like for you to take the derivative of this polynomial. What's the derivative of 1? 0. What's the derivative of x? 1 plus 2 comes out, x plus 3 comes out. You get 1/2 x squared, so could I write that x squared over 2? Plus 4 comes out. 4 over 24 is 1/6, so x cubed over 6 plus x to the 4 over 24 plus, and that is e to the x. See, it's itself. It's the only function that does that. That's pretty awesome. I mean, there is another function that does it. It's the function y equals 0, because the derivative of 0 is itself. But we call this the trivial case. This is a trivial function. And you could actually do it this way too. What's the antiderivative e to the x? Itself, right? Antiderivative of 1? X. 1/2 x squared. Keep going, right? It would work. Except what? We're missing the 1, but what do we always put at the end of plus c, and that would be 1. And That's pretty cool, right? No other power series will do this. This is the only one that works that way. Okay, so if you were to go on your calculator right now and you were to say, hey, what's E? You know, e to the first power. Everyone's like, well, 2.718 something on their calculator. Well, what your calculator is doing is it's plugging in 1 for x here. So if you plug in 1 for x on all of those, you would get closer and closer to what E truly is defined to be. All right, so there's a lot of things here in this chapter that are kind of suited for computer science majors because, you know, this is the way computers do this. You know, this is the way computers work. They work with power series. They don't work with, your calculator doesn't know what e to the x is. It knows that whenever someone types in that button and they hit a number in there, that they just plug that number into that, cut it off at some point. All right, we're going to start with sequences, though, which is 8.1. Notice the word sequence, not series. Now, I have actual notes that I'm going to go off of today. This is to keep me on track because I have a bad habit of getting off pace or off on tangents. So I'm going to keep myself grounded here. All right, so we're going to start with the definition of a sequence. A sequence is basically, in this class, a list of numbers. But in general, a sequence doesn't have to be numbers. For us, right now, it's going to be a list of numbers. Later on, it might turn into a sequence of functions, which would be a list of functions, right? We will write them this way. It'll be some number, a sub 1, followed by another number, a sub 2, followed by another number, a sub 3. And if this list actually stops, a sub n would be our last one. And this would be a finite sequence, what we call a finite sequence. We're not very interested in finite sequences because calculus is all about infinite processes. Right? We've cut up things. Integral, right, was cutting it up to an infinite number of little tiny pieces. Everything that we do in calculus is usually an infinite process. So, but we still need to know. Finite sequence is a finite list of numbers. Now, if I do not want it to stop, then I usually just put 3 dots, and this would become what we call an infinite sequence. Technically, the accepted thing is 3 dots, but you'll see me put like 4 dots, 5 dots. Doesn't really matter, all right? So an infinite sequence versus a finite sequence. So we look at it as just a list of numbers. I'll give you an example. Some of you have seen this one before. This infinite sequence, Fibonacci numbers, Fibonacci sequence. How does this sequence work? The first 2 are always 1. The next number is the sum of the previous 2. So 2 is the 1 plus 1. 3 is 2 plus 1. 5 is 3 plus 2, right? The next number should be 5 plus 3 is 8. The next one should be 8 plus 5 is 13. You just keep going with it. It's a very famous, very, very famous sequence. How many of you have seen the Fibonacci sequence? Okay. If you haven't, it's tied to what's called the golden ratio or the golden spiral. And we won't get into it. You can just go Google it. There's a lot of stuff out there about this. But it's an infinite sequence of numbers, okay? Now, some of you that have seen the Fibonacci sequence probably have never seen this one. I just learned about this one recently. I didn't know about it. Let's see if I can remember it.
Is it the same sequence, just differently?
It's a little different. Hold on. 1, 1, 2, let's see if I can do this. I might mess this up. Let me do this, hold on, 3, 5. It's the Fibonacci. You see the Fibonacci there? Yeah. But in between each of the numbers is the last number you added. So 1 and 1 was 2. Okay, so I added 1 and 1 to get 2, right? The next number I put here is the last number from here, so I should put 1. Then how did I get 3? 2. I added 1 and 2, right? So the last number I added there goes here. And then how did I get 5? I added 3 and 2, so the last number that go from there was what? 3, and then here, how did I get? 5, so 5. So I'm going to have to go back and look at it. I don't know if that's it. I didn't come in to talk. See, I'm already off on a tangent right now, okay? I believe that's called something like the Stern Bro Cot Sequence. But what that is if you create fractions out of all of these, like 1 over 1, the next one 1 over 2, and then 2 over 1, and then 1 over 3. Do you see what I'm doing? I'm making fractions out of them. Then that'll list out all the fractions that exist. It will only list each fraction will only appear one time, and all fractions will be in completely reduced form. If that's not the right sequence, I'm sorry, but go look it up if you're interested. Stern Bro Cot Sequence. It's a very interesting sequence because it shows that the fractions are countable. Because what you can do is you can walk through this and you will cover every single fraction. No fraction will be repeated and everything's reduced. So like you'll never see 4/8 appear in there because 1/2 will be in there and that's fully reduced. So you won't see 4/8, you won't see 8/16, you won't see 5/10. Interesting. But okay, it's an adapted form of the Fibonacci sequence. Stern Bro Cot, if you're interested. Saw that on number file. Okay, but we can get fixated on the idea of oh, it's just a list of numbers. I want us to look at a sequence as being a function, all right? So a sequence is a function where we have, do you remember this notation here back from college algebra? We have like input, output, output. And so the function would basically take something and spit out something. If I gave us a function back in college algebra, like f of x equals x squared, then you could start plugging in values of x. These would be your x's, and then the outputs would come over here, right? But there was really no restriction on x, was there? It was like, okay, you could plug in 0, you could plug in 1/2, you could plug in -10, yeah? A sequence is a function where we have restricted the inputs to only be positive integers. You can only plug in 1, 2, 3, 4, 5, 6. That's all you're allowed to do. And the output can be any real number. So it's kind of like, look back at this. Back in college algebra, if I would say to graph this function, you would graph a parabola, wouldn't you? You would graph this. But if I say now, just treat this as a sequence, you're not allowed to plug in 0, are you? You're not allowed to plug in -1. You're not allowed to plug in fractions. You can plug in 1 though, right? So you'd plug in 1 and it would spit out what? 1. And then you plug in 2, it would spit out 4. Plug in 3, it would spit out 9. And so what you get is instead of a nice, smooth, continuous curve, you're just getting dots, aren't you? Just a bunch of dots. That sequence of dots is your sequence. So if I were to list out this sequence right here, it would be the sequence 1, 4, 9, 16, 25, right? Dot, dot, dot. That would be the sequence that would come from this if I restricted its domain. Notice that I don't have to tell you what the input was. You know what the input was. Why? Why do you know I plugged in 1 here? Because 1 squared is 1. How do you know 2 here? But for any sequence, you're going to know that this is what you got when you plugged in 1. This is what you got when you plugged in 2. This is what you got when you plugged in 3. Understand? So you don't need to tell me what the inputs were. It's understood. So this is your A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, and so on and so forth. Agreed? So I could write this, if I wanted to write it as a function, I could write f of x equals x squared, but then I need to somehow tell you not to plug in anything except 1, 2, 3, 4, 5, 6, 7, right? So how do I tell you that? Well, one thing we can do is we can say, instead of using x, we'll use n. And then n, we just all understand and agree, is an integer, positive integer. All right? So we could write that this way. N is an element of, how do we say integers? Integers is a double struct z. And then how do I say positive integers? A little plus on top. So I could write that, and then that would tell you, hey, look, everyone, it's your standard x squared function, but you're only allowed to plug in positive integers. And wouldn't this create this list?
Yeah.
Understand? We still don't like that. Okay? Instead, we just write this. A sub n equals n squared. That's what we write. Now just think about that. Come out here. What would my nth one be? Well, the first one is 1 squared. The second one is 2 squared. The third one is 3 squared. The fourth one is 4 squared. The nth one is n squared, right? So the n squared would correspond to that one. So that's what we're going to write. The nth one is n squared. A sub n is n squared. That is the way we write sequences. That is the way we define them. This is the notation we use. Make sense? All right. Now, when we list out a sequence, a lot of times we put the sequence in braces. So we often use braces for sequences like this. This is an infinite sequence, right? Yeah. Okay. So if someone gave you this sequence and said, hey, can you give me the formula for that? Could you look at that and tell me what the formula is? You would say a sub n is n squared, right? So this is it written as a list. Written as a function, you would say a sub n equals n squared. Yeah? Okay. Sometimes you will see people put a brace around this too. I don't, but you might see some books do that. Just don't be surprised if you see it, all right? Now I want you to take and think about this one. What's the difference?
Stop.
Stop. It's finite, right? How am I going to tell you it's finite when I write it down as its function form?
X is less than or equal to 6 or 5?
X,
A is n.
n, a, n, x, what?
N.
N?
N is less than.
You need to tell me that you need to stop at n is 5, right? Yeah, that's not yet. Yeah. Okay, so How do I tell you that I need to stop 5? So there's a couple of ways we could write this. I could write a sub n equals n squared, right? And I could write n less than or equal to 5.
But you also put 1.
Do I need to say greater than or equal to 1? Not if we understand that n is going to start at 1,
Yeah.
right? Pardon? And it's positive. So these are things that, how much can we assume, Now, but this is, again, this isn't notation that we like to use. So let me show you what we would prefer to write here. What we write is this instead. See if you follow this. N squared. The braces means it's a sequence. N is 1 to 5. Does that make sense? So up here, if you just write this, take this one. If I just write this, that's an infinite sequence. Because I didn't tell you where to stop it, right? Start it or stop it. Here, I tell you where to actually stop. Start and stop. You okay with this? How about this one? No. I would like for us to write that out in its formula form. So how would you write that in its formula form?
N squared, 3 6.
You could go n squared,
N equals 3.
n equals 3
That's how.
to 6. You agree with that?
Yeah.
I agree with that. That would work. Now here's your challenge. Can you write that as a sequence that starts at 1? Like, can you not put this restriction at starting at 3? Can you somehow write this so that it's some sequence and it starts at 1? And you'll have to figure out where to stop it, but can you do it? So maybe it'll help if we write down these numbers. This is what? 3 squared. This is 4 squared. This is 5 squared. This is 6 squared. I need this one to be a sub 1, a sub 2, a sub 3, a sub 4, right? How do you get this to work?
Say n plus 2
N plus 2 squared. N plus 2 squared will work. So what you're recognizing, I think, is that when you plug in 1, you need that base to be a 3, right? When you plug in 2, you needed that base to be a 4. When you plug in 3, you needed that base to be a 5. When you plugged in 4, you needed the base to be a 6. So whatever you're plugging in, you need 2 more than that, right? That's kind of what you're thinking? And then just square each one of them. So whatever I plug in, if I plug in 1, I add 2 to it, and then I square it. Now, if I do that, where do I have to stop? At 4. What this means is that there is not a unique representation for a sequence. If someone gives you a sequence, you may have one representation, you may have another, you may have another. They may all make the same sequence, but it may look different. Okay? Questions? All right. We're going to continue doing this for a while. I'm going to give you a sequence and you're going to have to come up with a formula. Okay. How about this one? I don't want to push too hard yet. This is not a trick question. So is it infinite or finite? Infinite. So you're not going to have to worry about starting and stopping necessarily, right? Any ideas? A sub n equals? What do you need to get when you plug in 1?
1.
And when you plug in 2?
2.
And when you plug in 3?
Is this n?
N. That's it. A sub n is n. It's about as easy as it's ever going to be right there, right? You plug in 1, you get 1, 2, 2, 3, 3. Yes? Y'all are looking at me like crazy. Oh, because I'm missing 4. Sorry. Oops. Okay. I'm glad that y'all were giving me the look of confusion because you had a right to. Okay. Yeah, okay. Sorry about that. I'm like, come on, this is going to be a long couple of weeks if they don't see that one. All right, no, okay. That's okay. Whew. All right, we all woke up a little there. All right, how about this one? Now, I said you couldn't plug in negative numbers, but nothing says you can't get negative numbers out. N minus 7? What do y'all think? You like it? Does everyone like it?
Yeah.
I mean, look what's happening. You're still counting by 1 each time, right? You're still increasing by 1 each time, which is what you were doing here. Except that instead of starting at 1, you need to start at negative 6. So that means when you plug in 1, how do you get to negative 6? You subtract 7. When you plug in negative 5, how do you get to, when you plug in 2, how do you get to negative 5? You subtract 7. So isn't this list shifted left 7?
Right.
Yes? And that's where that formula would come from. Does that make sense? All right, how about this? N times 2? 2n? 2n? So 2n generates even numbers, right? This is an important one, all right? We're going to want to generate even numbers quite a bit in here. So just remember, 2n is what does that, all right? All right, let me try this. Can you generate the odds for me?
Two n minus 1.
2n minus 1?
Yeah.
Like this?
Yes.
Isn't every odd number here each of these even numbers with 1 taken away? So, 1 is 2 minus 1, and 3 is 4 minus 1. So it should be the same as this formula, just minus 1. Do you see again how that's working? Now, how about this one?
N minus 2.
Close. Close. 2n minus what? 2n minus 4. So let's see. If I plug in 1, I get 2 minus 4, which is negative 2. If I plug in 2, I get 0. When I plug in 3, I get 6 minus 4 is 2. Yes, but again, isn't it just this list, right? Take away 4 from each number. So if I take away 4 from this, I get negative 2. Take away 4 here, I get 0, 2, 4. So I want, again, for you to look at it as like you're moving. You're shifting this list around. Oh, yeah, this list is also important, the odds. How about this? 11, 13, 15. What is it? What, all of those numbers are what type of numbers? Odds. So it should be based on this list right here. Right? These are your odds. How do you get from 1 to 11? You have to do what? Plus 10. How do you get 3 to 13? Plus 10, 5 to... So you should just do this formula plus... How much are we adding to get up? Oh, you're saying final answer, plus 9. It's this formula plus 10, which would be 2n plus 9. Right? So 2n plus 9. A sub n is 2n plus 9. All right, I think maybe one more before we start getting crazy. It's not going to get too crazy, actually. How about this? I think you can do this, and this one's not hard. Two n minus 2. I just wanted you to see, that looks a lot like even numbers, right? So you might be thinking 2n, but you have to start, I wanted it to start at 0. So when you plug in 1, you get 2, so you have to take 2 away to get back to 0. So 2n minus 2. Okay? All right. Y'all are doing great. Okay, how about this? Keep it simple, Robert. Keep it simple. Got quiet in here. It alternates signs, doesn't it? We call this an alternating sequence, but we'll get to that in a second. Do you have a formula for it?
You still start at 1?
Still start at 1. Everything's still the same. 1, 2, 3, 4 gets plugged in. What does any of it look familiar?
Yeah.
What? Oh, God damn it, Robert. I screwed this up. Sorry. I'm just having one of those days, I think.
There you go.
Yeah, I'm sorry. I'm sorry. I'm having one of those days. You know, those happen sometimes. Immortal? Is that what you said? Oh, okay. Yeah, I'm going to make this harder than it has to be if I can't get this, put these things up here correctly. Okay, did that help at all or no? Does it look familiar? What does it look like? It looks like what? It looks like the odds, doesn't it? It's the odds, basically, except they keep switching signs on us. Right? So would you agree with this part so far? 2n minus 1, that would create just the odd numbers. So if I ignore the signs, that's going to create me 1, 3, 5, 7, 9, 11. Yes? All I have to do now is make it switch signs. And there's a way to do it.
Is it like notation? Or is it,
Absolute value.
that's the odds
Won't necessarily work because the absolute value of something that's positive is already positive. What else? Raise this to the. That'll. So what? Negative 1
That wouldn't
to the n?
Yes. That would alternate.
Oh, yeah. Okay.
Right? Think about this. What's negative 1 to the first power? Negative 1. What's negative 1 squared? 1. What's negative 1 cubed? Negative 1, negative 1 to the fourth. Positive 1. So what's going to happen here is this negative 1 to the n is going to control my sign. Right? That's negative 1 to the n is a big thing. We're going to see a lot of it. All right? That works, right? Okay. So what would be the difference between that and this? Make sure I get it right here. You could add a negative to the front of this, right? And that would change them all back? It would reverse them? So I'm listening to what's being said here. I could put a negative in front of this, right? Couldn't I do that? But this is really a negative 1, isn't it? So aren't I really just doing negative 1 times negative 1 to the n? And isn't negative 1 to the first power times negative 1 to the n power, you just keep the base and add the exponents? So isn't this negative 1 to the n plus 1 times 2n minus 1? Yes? Now that's, I didn't want to do it this way. What I wanted you to think about was when we started here, we knew negative 1 to an odd was negative, negative 1 to an even was positive. And we're always going to start with 1 here. So if I use this, I will always start with a negative, won't I? How can I change that? What I can do, so what I'm asking you to do is forget this for a second. What I can do is instead of using n, when I plug 1 in here, right, if I add 1, it moves that whole thing over by 1. So instead of getting a 1 out, I'm getting a 2. So my first input of 1 spits out an even instead of spitting out an odd. Understand that? And then the next time when I plug in 2, I get 3, and that will give me a negative, and then positive, then negative. Do you all see that? Would this have worked? So plug in 1, what do you get? 0. What's negative 1 to the 0? 1. So you'd have a positive in front, right? So either one of these would have worked, right? Could I have done this? That'll work also, right? Because if I plug in 1, I get 4. The whole thing is when I plug in 1, I need to get even. And then from there on out, it's going to switch. Odd, even, odd, even, odd, even. So there's actually an infinite number of representations of this, isn't there? The ones that we like to stick to are, well, we're going to use this a lot. We're going to use this a lot. Sometimes we'll use that. We seldom use this. It's usually one of those or that one, depending on what we want to do. Y'all still all right? All right. So this is known as an alternating sequence. Anytime you have a sequence that switches signs like that, it's called alternating. Well, I'll give you one more. Hey, let me double check. Yeah, that's good. So the way that we're going to go about these is we're going to do it a little more systematically now. Is it alternating?
Yes.
Yes. So let's start with creating the alternating. Let's just create the alternating part. You want it to alternate. You want it to start with a positive, right? So what should I use? -1 raised to the n plus 1 or n minus 1 would have worked also, or n plus 3 or n plus 7, n plus 121. It doesn't matter, right? As long as you get an even that first time through.
You start with a negative, you put a negative out there in front?
Where?
In front of the, alright, in front of the 1?
If you start with a negative, you just do to the end. So that's perfect.
Okay.
Yes,
Yeah.
to the n. All right, so that's, I don't have to worry about the signs changing anymore, right?
There you go.
The next thing I'm going to do is I'm going to look at these fractions. I'm going to try and look at the numerator and denominators separately. I'm going to see if I see a pattern in the numerator and denominators.
2n plus 1.
Okay, so I'm hearing two different things, two different sides of the room. Numerator pattern is what?
Plus 2 equals
Even numbers starting with 4. How do I create even numbers starting with 4? 2n plus 2, okay, divided by. Now, denominators were powers of 5. These are powers of 5, aren't they? 5 to the first, 5 squared, 5 cubed, 5 to the fourth, right? 5 to the n. We're done. Now, let me just show you. You could do more to this, okay? You could clean it up. I'm happy with this, but just so you can see it, I could do -1 to the n times -1 times 2n plus 2 all over 5 to the n. And the only reason I'd want to do that is that these two are both to the n power, so I could put them into a fraction together, and I could write them as what, -1 over 5 to the n? So I could write -1/5 to the n times 2n plus 2 all over, oh sorry, I don't have a fraction anymore down here. Sorry, 2n plus 2, but then negative. So these two go together to this, right? The -1 is out here, and then this is right here. That's another representation. It's just cleaning that up, making it look different. I would just be happy with this, all right? Hey, do any of these fractions reduce?
No.
Let's see. The last one, right? What does the last one reduce to be here? 5 goes into both?
Yeah.
So I could have written this as what? 2 over 125? Huh. I wonder if you would have figured it out if I had written that instead. You don't think so? I think you could have. Let's do that now. Let's think through it. You try and find a pattern, right? You go, okay, it's alternating. -1 to the n plus 1. Okay, got that. The top, they look like evens except that one, right? So you say, okay, let me just try and make the evens, 2n plus 2. The bottoms, they look like 5 except for that one. And then you say, okay, this is what I get when I plug in 1, 2, 3, and then 4, right? If you plug 4 into this formula, you will get this, right? You have to almost like go check and kind of reverse that simplification from your. Does that make sense? If they simplify the fractions, it can be really tough to get the formula. They could, yes. I'll give you an example out of the book. Where's one here? I thought there was one in here that was good. Maybe not.
You have to memorize the formula.
I don't see any in here that are real tough, so. All right, we'll move on. There's something that we use a lot in Chapter 8, Factorial, and you've probably seen this if you've been in a statistics class. Where else have you seen it, if anyone has seen it? A math class, yep. College algebra, probably. Okay, so factorial. Factorial is written this way. We use the letter N with an exclamation point, and it is defined for n equals 0, 1, 2, so non-negative integers. And here's the definition of n factorial. N factorial is equal to n times n minus 1 times n minus 2 times n minus 3, all the way until you get down to 1. And that looks really weird until you see it, like an example. So like 5 factorial, what's n here? 5, so it's defined, right? I can do this. This should be 5 times, take 1 away, 4, take 1 away, 3, 2, 1. That's it. 5 times 4 times 3 times 2. And then you multiply it out. You actually do the multiplication. And what do you get here? 120. Okay? Yes? You don't have to do the times 1, but just what do I put at the end then? Like, why do I tell you to stop at 1? I mean, how do I tell you to stop? You know what I'm saying? That's why I put the 1. You don't have to write 1 when you're doing it here. But I put it here because you go down till you get to 1. You could if you want. If you don't like the 1, then you could put,
Wouldn't it still be the same?
what?
If you stop at 2?
You could stop at 2. Sure. There's no difference. I mean, but what if it's, so let's not get into it. Let's not get into it. That's the way we wrote it down. All right. All right. So what is 4 factorial? 4 times 3 times 2. 2 times 1, which is 24. Anyone recognize these numbers? 3 factorial, 6. What's that? I know, but I said, does anyone recognize these numbers? 2. From somewhere today? Look up there. You see the denominators in those fractions? 2, 6, 4, 120, 720. Do y'all see those? 2, 6, 24, 120, 720. All those denominators for e to the x are actually factorials. But we're getting ahead of ourselves. The next natural question would be, I said it was defined for 0, right? So then what's 0 factorial? It's defined to be 1. I know that doesn't make sense. You're just going to have to take that one on faith for now. No, because you're supposed to go to 0.
No, but like when you do the factorial equation that you wrote, it stops.
Yeah, but if 0 times anything should be, yeah, so let's not get into it. Did you have an explanation? Someone had an explanation? No? Okay.
It's like yesterday, Tuesday, you told us about adding the polynomial.
Oh, yeah, yeah. Well, this one is actually just, we do it by definition. Anytime you see an equal sign